variable size reduction. All right. Yeah. Yeah. Before I start this topic, first let me say a few things, comments from our last topic. Last time we finished. Yeah, so this time I need to use my second computer to bring Grant. Grant just joined us. All right. Then my first computer. All right. Yeah. All right. So here, let's recall the problem we just solved last time. So remember a little bit. The problem is the Tower of Hanoi problem, right? Yeah. Tower of Hanoi problem. Yeah. So this problem. Yeah. So we just complete the solution. Yeah. So let me make some comments. All right. The first question is, so here we are talking about the n-disk problem, the general n-disk problem. Yeah. In our example, we did n equals 3 case. Yeah. So I drew the diagram. When n equals 3, the number of moves equals 7, right? 7 moves, yeah, from the diagram. Yeah. Yeah. And the question, when n is a general n, what is the number of moves? How many moves for the general case? How many moves? Yeah. Yeah. But today here, I do not want to explain how to find the number of moves. I leave to the part D, part D of module 3. Yeah. Because we need to solve a recurrence relation problem. Yeah. So I delay this question. Yeah. But I can give you the answer to that question. All right. Yeah. Answer. All right. Yeah. To get that number, can you connect these two numbers, 3 and 7? What's the relationship? Can you see that? 3 and 7? Yeah. So here you can see 7 equals 2 to the third minus 1. 2 to the third, that's 8. 8 minus 1, 7. Yeah, that's the relationship. Then for the general case, later we will show it. Yeah, so here you can guess 2 to the n minus 1. This many moves. That's the general case. All right. So here you get an idea. Okay. When n is small, this number not that large, right? Yeah. When n equals 3, this number is 7. It's not very large. But now, when n becomes larger and larger, then the number of moves increases in an exponential function. Okay? Yeah. Remember? So what is the growth function? Growth function, we can drop minus 1, right? So 2 to the n, it is the growth function. Growth function. This large. So this is an exponential function. So you can see the number of moves increases as an exponential function. Yeah. So that means increasing very fast. Yeah. Here, to give you some idea how fast it increases. Yeah. It's very interesting. Think about last time I mentioned a special case, that is n equals 100, right? When n equals 100, how large is this number? So when you have 100 disks, in order to solve that 100 disk Tower of Hanoi problem, you need to make the move, this many moves, 2 to the 100 minus 1. This number. Do you know how large is this number? How large is this number? Huge number, right? Yeah. But how huge it is? Do you have an idea how huge it is? Yeah. So here I'll give you a simple example how huge it is. Yeah. Let me give you a reference number. Reference number. Yeah. So the reference number is this number. The number of sands on Earth. The number of sands on Earth. This number. How large it is. The number of sands on Earth. Okay? All right. So if you search the web, you can get this number. It says 75 times 10 to the 17th power. Okay? Yeah. You got this number. This number gives you the number of sands on Earth. Yeah. But here, because to compare that number with our number of moves in the Tower of Hanoi problem, yeah, so we do the conversion. Yeah. So if you do conversion, this number can be converted to approximately 2 to the 63rd. This number, 2 to the 63rd. That number. Okay? Yeah. Yeah. So here, actually, I increased that number. Okay? Yeah. Because this number, I can write it as 7.5 times 10 to the 18, right? 7.5, I use 8 to replace it, right? Yeah, so then 10 to the 18. 8, that is 2 to the 3rd, right? 10 to the 18, that is 1,000 to 6, right? We know 1,000 approximately equal to 2 to the 10th, right? 2 to the 10. 1024, very close to 1,000. So very close to 2 to the 63rd. So that's the, how I get this conversion. Yeah. And you can see the number of sands on the Earth, this number, much smaller than the number of moves for the Tower of Hanoi problem with 100 disks. Okay? Yeah. So the number of sands on Earth close to the number of moves of the 33 disk problem, right? 33 disk problem. Okay? So you can see, yeah, so that number is much larger than the number of sands on Earth. So you can get an idea how big is that number, and especially how fast a number can grow if it increases in an exponential rate. Yeah. So yeah, you get that idea. Okay. All right. Yeah. So that's the comments I want to talk about. Yeah. Will this be on midterm? All right. Yeah. Here, let me answer a general question. Everything appears in our notes. Oh, you mean this part B? Yeah, part B will be included. Okay. Our midterm contains module 1, module 2, and part A plus part B of module 3. Yeah. So this part, because we covered, so it is included in midterm. Okay. Yeah, including today's lecture. Yeah, but after today's lecture, not included in the midterm. Yeah, yeah. So you can expect everything appears in the notes. No, it's you know, there is a possibility to appear in the midterm. Yeah, including this question. Okay, Tower of Hanoi problem. Yeah. All right. Yeah. So let's start our problem 9. Count binary digits. Given a positive decimal integer n, find the number of binary digits. Now, binary digits we call the bits, right? Yeah. So bits. Yeah. In its binary representation. Yeah. Yeah. So this question related to the topic of this part, variable size reduction. Yeah. All right. Yeah. So let's do the analysis. First, let me recall the binary representation. Now, in the discrete math, you learned binary representation. Yeah. Here, let me give you the formula. The formula is this. Yeah. And here you can see, because it's binary, so we use the base 2. The base is 2. Okay? Yeah. If for ternary, we change base to 3. And in this way, we can use any, let's say, canary. Okay, canary, K, base K. Base K, we can use, similar representation for the, canary representation. Yeah. So here, the binary representation. The binary representation, the B, so BI can only take 0 or 1. 0 or 1. Yeah. Yeah. Bits. Yeah. And our last bit, or because the bit number B sub S, that bit number corresponds to the most significant position, right? Yeah, because this is the, corresponds to the largest power of 2. This is the most significant. No most significant bit, we can assume it's non-zero. Yeah. Because otherwise we will change that S. Yeah. If it's 0, we look at a B sub S minus 1. That will become the most significant bit. Yeah. So this is our assumption. Yeah. All right. So here you can see, after we assume this B sub S equals 1, yeah, our goal, we need to find the number of binary digits, bits in its binary representation. Then we just count the number of B coefficients, right? Yeah, because that's the number of bits. Yeah. So number of B coefficients, the same as the number of bits, right? Yeah. So the answer, we can write the answer S plus 1. Yeah. But that cannot be our final answer. Yeah. Because here we use a S. Yeah. Our final answer should be in terms of n, not S. Yeah. Because the n number is given, right? Yeah. Given. When the question given, the n number is known. Yeah. And furthermore, that n number, yeah, because it's given in the problem, that n number, remember, I introduced a concept before. Yeah. So here, this n number also connect to a concept we learned before, that is the problem size. The problem size here is that n. Yeah. Yeah. So we saw this concept before, the problem size concept. But at that time, the old meaning, yeah, old meaning we have that meaning is the number of elements in the array. That's the old meaning. Yeah. But here the meaning is different. Okay? Because here we only have one number. We are given only one number. So here the problem size in this place, it's not the number of elements in the array. Okay? We only have one number. So the meaning of the problem size here changes to a different meaning. So how different? It's the magnitude of the number. Magnitude of the number. Yeah. So it's the second meaning of the problem size. Yeah. Now later we will have a few questions. We use the magnitude as the problem size. Yeah. All right. Yeah. So here, when you want to represent your answer, you should use this n number. Okay? Yeah. So you need to, in other words, you need to represent S in terms of n. S in terms of n. Yeah. From n. Yeah. So in order to find S from n, yeah, based on this binary representation, yeah, so we need to derive a recurrence relation. Yeah. So then we need to find a solution of this recurrence relation. So we solve this problem. All right. So the insight, the question, insight for what? Insight for the recurrence relation. Because the goal, we want to find the recurrence relation. Recurrence. Okay, yeah. Derive that. Yeah. All right, so here we need to do some transformation on this formula. Yeah. All right. So you need to do some special operation on this formula. Yeah. So how special? We do the division operation. Do division. Division by 2. Yeah. So what division? Division by 2. Integer division. Division by 2, but here we do integer division. Okay? Yeah. Only keep the integer part. Integer division. Okay? Yeah. Drop the fractional part. Yeah. All right. So let's do division by 2, both sides. Yeah. Left-hand side, yeah, because we need to drop the, the fractional part. So we take the floor function. N over 2, then we take the floor function, so we only keep the integer part. Left-hand side. Right-hand side, yeah. Only the first term, B0, when you do division by 2, that may result in the fractional part. And all the remaining terms, because all these remaining terms, when you do division by 2 operation, they all have integer results. Yeah. So then here, B0 after division by 2, we drop. So including the B1. Okay. Yeah. So that B0 part after division by 2, we drop it. Okay, we drop it. Yeah, because only 2 cases. Yeah, that B0 part, only 2 cases. The first case is 0. Yeah, B0 equals to 0. Division by 2 also 0. Second case, 1/2. Right? Yeah. 0, nothing. Yeah. All right. 1/2, this case, less than 1. Yeah. Because that's the fractional part. So we drop it. Okay? Yeah. All right. Then, from this new formula, yeah, so this is our second. From this new formula, can we derive a recurrence relation about n? Yeah, so this recurrence relation should be about n number, okay? N number, yeah. Not S number, N number. Because our final answer should be in terms of n, not s. So when we derive the recurrence relation, that recurrence relation should be in terms of n, not s. Okay? Nothing to do with s. N. Yeah. All right. So now, observation. Yeah. Yeah. So what's that? All right. First, yeah, least significant bit is removed. That's the B0. Okay, B0 is the least significant bit removed. Yeah. The number of bits is reduced by 1. Yeah. So when you count the number of bits, yeah, because this bit is gone, B0 is gone. And all the other bits remain. Yeah. B1 through B sub S. All those bits remain. Yeah. So if you count the number of bits, that number is S. Okay? Yeah. From 1 through S. So it's S. The reduction, because before we do division by 2, that's S plus 1. S plus 1 reduced to S. So that's the reason that number of bits reduced by 1. Yeah, so that's our observation. Yeah. But when we write our final formula, we cannot use S. Yeah, we need to use N. Yeah. Yeah, the problem size reduced by half. Yeah, I just talked about the problem size, okay, the magnitude. Problem size. Yeah. Problem size. What's the problem size? Yeah. The problem size is n over 2. Yeah. So the problem size here is floor function of n over 2. Floor function of n over 2. That's approximately n over 2, right? Yeah. We know. We use approximation very often. Yeah. So it's approximately half. Yeah. Yeah. So reduced by half. Yeah. So based on these observations, now we can derive that recurrence relation. Yeah. All right. So the final formula is like this. Yeah. Yeah. We define a function. So the function here we call bin rec. Yeah. Binary recurrence of n. Yeah. So the left hand side of the function. The function means the bits. This function. Yeah. Bits in the binary representation for a given number n. Yeah. Right hand side, yeah, because the problem size reduced to n over 2 floor function, so we apply the same function, but we use the new size, new problem size here, and the difference is 1. When we apply the function of on that half problem size, approximately half problem size, then these two numbers, their difference is only 1. Okay? So we derive this recurrence relation. Yeah. So the next question is, we need to solve this recurrence relation. Yeah, because this recurrence relation does not give us the final formula. It's not a final formula. So the solution should be the final formula that is a function of n. That is a known function of n. Yeah. So the final answer, yeah, the final answer must be a known function in terms of n. Okay, that's the final answer. Yeah. All right, so let's find the solution next. Yeah, and we need a base case. This is the base case. Every recurrence relation must have some base cases. Yeah, here we only have one base case. Yeah, and later you will see sometimes we need more than one base cases. Yeah, later more than one base cases. Yeah, here one base case is enough. Yeah, all right. Next, now we need to solve this recurrence relation. Yeah, all right. And this division by 2 in computer science, we know we do left shift operation. We shift the binary point to the left by 1 position because the shift operation is very fast. Yeah, faster than addition. Yeah, because the shift operation, you only move the digit by 1 position. That's very faster, even faster than addition operation in computer science. Yeah. All right. Yeah, because that shift operation is faster than addition operation. Addition operation is slower. Yeah. So here, when we do the counting, so let's count the number of additions. Okay, yeah. How many additions we need to do? Yeah. All right. So we treat that addition as the basic operation. Yeah. All right. So let's define new function, simpler new function, a of n, capital A of n as the number of additions. Our goal, we want to count. How many additions we need to do? So a of n. All right. So we get a recurrence relation. With this new function introduced, then we want to derive a recurrence relation using this new function n. Okay. All right. So let's do the, So you can see we get a similar recurrence relation from the left-hand side. All right. So the meaning is like this. When n equals 1, a of 1 equals 1, because we treat this corresponds to 0 plus 1 equals 1. So one addition, okay? One addition from 0. Starting point is 0. Or the starting point, we can say a of 0 equals 0, okay? Base case. Then, for the general case, left-hand side, a of n, number of additions for given number n. So left-hand side, we applied the a function, capital A function. The right-hand side, based on the, the previous recurrence relation, because we need to apply that recursive function on the half problem size. And based on the definition of A, the number of additions should be capital A of this number. All right. Then after that, you need to add another addition, plus 1. You add one more addition, plus 1. Okay. So you get the recurrence relation. Although these two functions different, bin, rec, and a function, these two are two different functions, but you can see these two functions are the same functions. Mathematically the same function. Okay? Meaning, definition, different. So their meanings, how we define these two functions, they are different. But mathematically the same, that means they should have the same math formula. These two functions should have the same math formula. So now we only need to derive the second math formula for capital A of n. Because that's the same formula of the, the first recursive function formula. All right. To do that, all right, so here. The question, how do you handle the floor function? Because when we need to solve this problem mathematically, we need to handle that floor function. That floor function, a little hard to control, right? How do you control that floor function? Sometimes you need to round it down, and sometimes you do not need to round down. When n is an even function, you do not need to round down. But when n is an odd function, you need to round it down, because you truncate the fractional part. So this little thing, although you do some small truncation, but that make the formula control very hard, right? That make the formula control very hard. A small change, very little small change, that make the formula control very hard. Because our final answer So here, the goal for the final answer, we need to get an exact formula, okay? Exact formula. Not an approximate formula. Not an approximate formula, okay? Yeah. So here the answer, we want to get exact formula. Approximate, yeah, that's different. Yeah. If approximate formula is there, you know, we can replace this flow function just by n over 2. That's a good approximation. Okay, good approximation. So in that way, to derive approximate formula, not that hard. Not that hard. Not as hard as exact formula. Exact formula, you cannot drop anything. Okay? You cannot drop tiny, small, little amount. You cannot. Okay? Yeah. So that makes the solution much harder. Yeah. All right. So here we need to work on that exact solution. Yeah. All right. So let's examine the property for even and odd case. When n is even, flow function of n over 2 equals n over 2 directly. Okay. No round down error. No round down error. Okay. Round down error. But the other case, there is a round down error. Okay. Small difference. The 1/2 difference. Rounded it down. Okay. Yeah. Yeah. So the question. Here we have two cases we need to consider, right? So in your solution, you need to consider these two cases. So the question, which case you want to work on first? Which case you want to work on first? Yeah. All right. The first case or the second case? Yeah. Remember, I mentioned a simple strategy before in problem solving. A simple strategy before. When we have several cases, we always work on the simplest case first. Here we should work on the simplest case is even case. When n is even, it's simpler. Yeah, so we should work on the simpler case first. Yeah. All right. Here, so let's assume, because when we work on the even case, we assume n is even number, right? Yeah. So when n is even number, we wish n is even. Yeah. But because this is a recursive function call, the next round, we need to do another division by 2 and flow function again, right? Flow function, we apply it on n over 4. Then you may have another round down error, right? You may have another round down error. What do you wish, right? Yeah. It could be very complicated, yeah, because you need to apply this recurrence relation many, many times. Yeah, every time you may get some round down error that make the solution harder, right? Yeah. All right. So can you imagine some special case that we do not have that complexity? Yeah, that's too complicated. So we want to avoid that complexity. Can you imagine some special case we can get around that round down error complexity? Yeah. So that's what we do in problem solving. In problem solving, the first time we always assume the best case that we can get. Here, what is the best case you can get? Yeah, think about that. So that's the idea I want to convey. What is the best case we can skip all those round down errors? That's we want to work on the first time. Okay, yeah. So here you can see we wish, all these n over 2, n over 4, n over 8, n over power of 2, all integers, right? Yeah. So the best case we can imagine, that is, we assume n is a power of 2 form. A power of 2. N is a power of 2 form. Has that form. Number. A power of 2 number. Okay? Yeah. Then we can ignore all the round down errors when we apply the recursive function. Okay? Yeah. So here, the first time when we try, we assume n is power of 2, 2 to the k. How about that? N is 2 to the k. Okay? So then k equals log base 2 of n. So let us solve this simplest recurrence relation. So the new recurrence relation, because all the floor function gone. So we want to get a new representation without any floor function. All right, so let's do the work. The first equation, like this. Second one, division by 2. Okay? And then we keep applying this recurrence relation all the way down to the last equation. So this is the last equation. Okay? All right. Then if we add all these equalities up both sides, we can do a lot of cancellations. So the first cancellation like this, that's kind of diagonal. Slant cancellation. Okay. Second cancellation, third cancellation, and so on. And then last cancellation in this fashion. Okay. After all the cancellations, you can see left hand side only this one number left. Right hand side only this 1a number left. But we need to accumulate all these ones. How many ones do we have? Can you see? How many ones do we have? You need to count the number of equations, the number of equalities. Can you see how many equalities do you have? The number of equalities. Remember, I talked about one counting method. That is the counting by reference, right? Counting by reference method again. Based on that number, you need to find appropriate reference, right? So for this equation, let us use the exponent number. Okay, the first equation. So we use all the exponent numbers as the reference. You can see, so each equation corresponds to the exponent number from 1 through k. So then the number of equalities, there are k equalities. There are k equalities. Okay? So that means there are k ones. Okay? Then, because this a of 0, the base case, a of 0 equals 1. This number equals 1. So you have total k plus 1 ones. So that a of 2k equals k plus 1. So you find the solution for the special case n equals power of 2. But you need to write your final solution in terms of n, not a k. Yeah. K is an intermediate variable. Intermediate variable. It's not the final variable we want to use in our final formula. So you need to go back to the n expression. When you go back to the n expression, left-hand side, just the a of n. Right-hand side, k, you should replace k by log base 2 of n, right? So the result, the final result, so you get the final formula, this a of n equals 1 plus log base 2 of n, but this is under the assumption n is a power of 2 assumption. Then you can have this answer. In other words, if n is not a power of 2, you don't know if this formula is correct or not. You don't know. Okay? Yeah, you don't know it. All right. So you only know when n is a power of 2, this formula is correct. For other cases, you don't know if it is correct or not. Okay? Yeah. So that's what we have at this point. But our goal is we want to find the general case solution, not a special case solution. So we need to do the last step, how to get a formula for the general case. In other words, how do we extend this formula to the general case? So we need to do extend it to the general case. Okay, we need to do this to the general case. Okay, yeah, all right. Then the general case. Now we need to talk about the general case. The general case. Okay. Here, we need to apply another strategy I mentioned last time. Yes, strategy. Okay, simple strategy, but very useful in our problem solving. So we apply those strategies again and again. Yeah, I hope you learn, after you learn these strategies, in your future problem solving, you can apply all these basic strategies. So what's that strategy? Here we need to use the guess and verify strategy. Guess and verify strategy. Okay, guess. When we extend it to the general case, the first step, you need to make your guess. Guess that formula. Guess the formula, okay? Guess the formula. Then we verify it. The question, how do you guess the formula? Okay? Yeah. This is a special case. Special case. We have a special case formula. From the special case to the general case, can you make a reasonable guess? Reasonable guess. Okay? Yeah. Because when you make a guess, you need to base on assumption. You need to base on known information. You cannot make some random guess. Okay? Yeah. Remember, last time when I talked about this strategy, guess and verify, I also mentioned when you make your guess, it should be as close to the true answer as possible. If it is far away from your true answer, then the remaining work will be too much. You need to do the remaining work, right? You need to bridge the gap. There is a gap. There is a gap between your guess and the true answer. If the gap is too big, then you need to do a lot of work. Only when the gap is very small, then You do not need to do a lot of work. Much easier to fix the gap. Yeah. So here, we need to make a reasonable guess based on the special case formula. Yeah. All right. We know the general case formula should be an integer function, right? Yeah. Because the number of bits, that number must be an integer. And this log function, for the general case, this log function does not give us integer expression, right? When we apply log base 2 function on integer n, most of the time we won't get an integer, right? Yeah. So here the question is, we need an integer expression, but this log function does not give us integer expression in general. Then there is a gap, right? Yeah, there is a gap. Yeah. The question, how do we fix that gap from non-integer log function to integer expression? That's the work we need to do. Okay? Yeah. How do you convert log base 2 function to an integer function? Do you know any simple way to do the conversion? Simple way to do the conversion. Yeah. So here, actually, we know there are two simple functions that allow us to do the integer conversion. The first one is floor function. Second one is ceiling function. Okay. So if we make one guess, there are two reasonable options for us. One is the floor function. Another is the ceiling function. Both integer representation. Yeah. But do you know which one is correct? Yeah. One must be wrong, right? Yeah. These two cannot be both correct. Yeah. At least one must be wrong, right? Yeah, at least one must be wrong. Yeah, it's possible both wrong, yeah, but we know at least one must be wrong. So here we want to eliminate that wrong formula. So we want to, these two options, we want to reduce it to one. Yeah. Can you tell me what is the idea to help us reduce one of the two options? Idea. How to reduce? When we have these two options, how do we reduce to one? Yeah. So here, another strategy we used before. Okay, so here you can see, yeah, simple problem solving strategy. Do experiment for when n is a simple number. So here, do experiment for n equals 3. Do experiment when n equals 3. Okay, yeah, that's easy, yeah, because when n equals 3, the binary representation is 1, 1, right? 1, 1, base 2. Base 2 representation, 1, 1 equals 3, right? Decimal 3. Yeah. 1, 1, there are 2 bits, right? So that means when n equals 2, the correct number should be 2. Okay, all right. Let's plug in. Yeah. For the floor function case, log base 2 of 3, yeah, log base 2 of 3, 1 point something floor, this gives us 2, right? Yeah. For the ceiling function, round it up, right? Round it up. Yeah. Log base 2 of 3, we know that's 1 point something. Okay, more than 1. More than 1, round it up, you get a 2. 1 plus 2, you get 3. Okay? Yeah. But we know the correct answer should be 2. That means the second option must be wrong. Okay, the second option must be wrong. Yeah. So then we shall only keep the first option. First, get that as our best guess. Okay, yeah. Let's say in this way, the first option is our best guess. Okay, yeah. All right. Then the question, how to verify it? Yeah. So you make a good guess. Okay, you made your best guess, but that's not a proof, right? The guess cannot be a proof. Yeah. So you need to prove it. Yeah. Prove it. Okay. All right. So here, I won't do the proof here. Yeah, it can be proved, but to prove it, we need to apply another important method. It's called mathematical induction. Mathematical induction. Okay, yeah. Yeah. So in a discrete math, you learn this mathematical induction. Yeah. Here, I can apply mathematical induction to prove this formula is correct. Yeah. But I need to do a lot of work. Okay, all right. Yeah. But the mathematical induction, I want to review. Yeah. So in this class, yeah, just because this tool, we treat this mathematical induction as a problem-solving tool, a tool very useful in problem solving. So I still want to, show you how to apply this tool. Yeah. But I want to reduce our lecture time a little bit, yeah, because later when we solve the Fibonacci numbers problem, we need to apply mathematical induction another time. Yeah. So on this problem, mathematical induction, I skip that. Yeah. So when we go to the Fibonacci numbers, that formula, then I show you how to apply mathematical induction. Okay. So I only do once. Yeah. Yeah. We need to apply mathematical induction 2 places. Yeah. But in order to save time, I only show you the second time. Yeah. The first time I skip. Yeah. So to save some time. Yeah. All right. Yeah. So here later by mathematical induction, we will show this is a correct formula. Okay. The guess one is a correct formula. Then we complete the solution. Yeah. All right. So this question, you can see we applied many problem-solving strategies, several problem-solving strategies. Yeah, at least 3, right? Yeah, at least 3. Okay. Yeah, 3 different places we apply some problem-solving strategies. Yeah. 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 So you can learn a lot of things from this example. Yeah. All right. Yeah. So we do not have much time left. Yeah. So here, this one, the size reduction is the half size reduction. Every time we reduce the problem size by 1/2 of the original problem size. So you can treat it as the half size reduction. Okay? Yeah. All right. Yeah. So then the next example, also problem size reduction, but that size reduction can change every time. Yeah. Every time. Sometimes larger, sometimes smaller. Yeah. Yeah. All right. So yeah. Yeah. So the general form, yeah. So that one, B.2, variable size reduction, sometimes more, sometimes less. Yeah. So that one is the greatest common divisor problem. Okay? Yeah. Find the greatest common divisor of 2 non-negative integers, m and n. Yeah. All right. Because that is a long story, so let me leave it next time. Leave it next time. Yeah. All right. Yeah. Before we finish today's class, before we go, yeah, starting next time, yeah, because we need to prepare for the midterm, right? Yeah. So we need to prepare. Yeah. So here, let me repeat that midterm. Right, as I mentioned last time, yeah. October 15th, Tuesday, yeah. So our new midterm time. Okay, yeah, new midterm time. Yeah, all right. Yeah, and then we need to do a review. Okay, yeah. So we need to do a review for the midterm. All right. Yeah. So starting from next class, we will do a midterm review. Right. Yeah. So the midterm we have. Starting from next, we have three classes. Yeah. So Thursday's class this week. Next week we have two classes before the midterm. So total 3 classes before the midterm. So we can do review R1, R2, and R3. Okay? Yeah. And some of the classes I only do. Some of the classes I do not need to use the whole class to do review. Yeah. Because yeah, so this question, problem number 10, we will complete it next class. Okay? Yeah. We complete it in Thursday's class. Thursday's class, we complete this topic first. After that, then we do review. So we do quiz 1 and 2. Okay? Yeah. In our next review class, we will do quiz 1 and 2. Yeah. Oh, I will open up the quiz answers. Yeah. Some students ask me. Yeah. I will open up the quiz answers for number 1 and number 2. Yeah. Then quiz 3 and homework. Yeah. Okay. Yeah. So this one, Q12, okay? This one, Q3. This one, review, talking about homework question number 1. Okay? Yeah. Yeah. That's our preparation plan for the midterm. Okay? Yeah. All right. Before you leave, if you have any homework questions you want me provide more helpful information, you can type them in the chat area. Okay, I will collect all your question numbers and I will make videos to answer your questions. Okay, all right. So you only have 2 chances, today and Thursday's class, to give me those question numbers. Okay, all right. Yeah, that's it.